Our Colligative Properties podcast is going to take us a little bit all over the place. So we're going to talk about what colligative properties are, and then we're going to talk about what changing the amount of solute in a solution does to that solution. So we'll talk about boiling point elevation as well as freezing point depression. In short, colligative properties are the properties of a solution that depend on the concentration of the solute, but not its identity. So how much of the solute is present in your solution? We don't care if it's salt or sugar or whatever, just the presence of the solute and how much you have will determine colligative properties. So the number of dissolved particles in your solute will affect the property. As you increase the dissolved particles, that increases the effect of the colligative property. Two terms we need to discuss before we get any deeper into this is the terms volatile and non-volatile. If something is considered volatile, a substance is volatile, it means it escapes readily into the gas phase or the vapor phase. So think about some of the substances you have that you open the container and you can instantly smell them. That's something that's volatile. It is escaping from the liquid phase to the gas phase, and you're detecting that with your nose. Immediately, I think of gasoline. When you're pumping gas, you can smell that right away. It's very volatile. It escapes to the gaseous phase. Acetone, so nail polish remover, the second you open that, very volatile. That escapes to gas. You can smell it. It's already in the gas phase. If it is non-volatile, it does not readily escape to the gas phase. So here we are seeing, and this is jumping forward just a hint, but let's go with it. In this image, we see water, and we see liquid water, and we see water in the vapor phase or the gaseous phase. And water is escaping to the gas phase. It's also recondensing and forming liquid again. So we have an equilibrium because it's a closed container. So some is escaping to gas, some is re-entering the liquid form. When we add a solute to this, so the solute is those purple spheres, less of the water is able to readily escape to the gas phase. That solute is kind of blocking it from escaping to the gas phase. So when we add a non-volatile solvent, or solute, excuse me, to a solvent, so something that doesn't readily escape to the gas phase, the vapor pressure of the solution above the solvent lowers. So when we say vapor pressure, we're describing how much gas is able to escape, how much of the solvent is able to escape to the gas phase. So this is a decrease in the water in the vapor phase compared to if we didn't have a solute present. So the more solute we add, the lower that vapor pressure would be. We'd have less and less water being able to escape to the gas phase. It's a colligative property. So when we dissolve a solute in the solvent, we're going to affect the vapor pressure, which we talked about on the last slide. And this is the amount of pressure a gas exudes on the surface of a liquid. So the vapor pressure will decrease with the addition of a non-volatile solute. So we saw that on the last page. As we increase non-volatile solutes, your vapor pressure is going to decrease because you have less of that liquid escaping to the vapor phase. It will increase with an addition of a volatile solute. So something, if you're adding something that readily escapes to the vapor phase, that's going to increase your vapor pressure. You're going to have more of that substance in the gas phase above the liquid. So here we see a volatile solvent, it's able to escape to the gas phase. As soon as you add that non-volatile solute, those orange bubbles, we get less that's able to escape into that vapor phase. All right, so again, another effect of adding a solute in a solvent is boiling point elevation. And it is exactly what it sounds like. So we're increasing the boiling point of a liquid by adding a non-volatile solute. So think about it. When we add the non-volatile solute, it is more difficult for the liquid to escape as a gas. Well, if your liquid is water and you add salt to it, it's going to take a hotter temperature and more energy to get it to escape to the gas phase. So it increases the temperature at which the liquid boils. And the boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. And as you know, here in Colorado, we have less atmospheric pressure, so we have a little bit lower boiling point for our water. Vapor pressure is lowered as there are fewer solvent molecules in the gas phase, and the amount of the boiling point increase. So how high that boiling point is increased is dependent upon the number of dissolved particles. It's a colligative property. It depends on the number of solute, not the identity. So think about this for a moment. Here again, we're seeing our image that's showing us the addition of a non-volatile solute. Let's say we're just taking water and we're adding salt to it. Well, that salt is non-volatile. It's not going to escape to the gas phase. It's preventing the water from escaping as readily to the gas phase, which means it's going to take more energy for it to boil, which is why we add salt to a pot of water for pasta. Okay? You're cooking the pasta faster, not because you added salt. Well, because you added salt. Because you are increasing the temperature at which the water boils. So it's boiling at a hotter temperature, which means you're cooking the pasta at a higher temperature. It's cooking faster. The more salt you add, the higher the boiling point, the faster it cooks. But I warn you, if you add a cup of salt to your pasta water, nobody's going to eat your pasta. There is a sweet spot for that, so be careful with that. Ooh, I'm giving cooking tips too. I'm doing it all. If we can add solutes to a solvent and increase the boiling pressure, we can do the exact opposite. We can add solute to a solvent and we can decrease the freezing point. It is something that I call freezing point depression, or December in Colorado. So we're decreasing the freezing point by adding solute. The presence of the solute makes it more difficult for the solvent to form a crystallized form. So to go from a liquid to a solid, to freeze, okay, your molecules are going to have to move and form an orderly structure. If you have a solute in there blocking that formation of the crystallized structure, it's going to take a lower temperature for it to freeze. It's more difficult. So the amounts of the freezing point decrease depends again on the number of dissolved particles. The more solute I add, the lower temperature it's going to freeze at. So think for a moment about when we get icy sidewalks. We will sprinkle an ionic salt on there. We'll use magnesium chloride and we'll sprinkle it on there. We're not using the salt to melt the ice. We're using the salt as a solute to disrupt the freezing of pure water. So now it can't freeze solid at that temperature. The temperature is going to have to drop even lower for that to freeze solid. So you've decreased the freezing point of water, not melted the ice. It's liquid because its freezing point is lower. Blows my mind. We also see this used in plane de-icer. So airplane wings are de-iced and the solution that they spray on there is not water, or else it would just freeze and that would be pointless. But it is a solution that has ethylene glycol, which we know familiarly as antifreeze, which again, it has a colligative property. You add in the antifreeze, it lowers the freezing point so the ice melts because it's not cold enough for that liquid water to turn to ice. So that is freezing point depression. This handsome fishy is called the rainbow smelt, or Osmorus mordax, and it is distributed more in the northern states across the United States, also into Canada. They have reported them in Colorado, but it's a really neat little fish. So this fish will actively feed under ice at temperatures as low as the freezing point of seawater. Think about that. If it's seawater, it has a higher concentration of salt, which means the freezing point of that is really incredibly cold. And this little guy can just swim through and go on with life as normal. And the way that it is able to avoid freezing itself, because you would think it would, I would freeze solid. It's avoided through the production of an antifreeze protein. So this protein does not have colligative properties, so it's not a solute-based protein, but this protein keeps it from freezing, and then also produces glycerol. Glycerol does act in a colligative manner. So as you increase glycerol, which is a solute, it decreases the freezing points of that liquid. So this little guy is excreting glycerol onto his skin, and that's keeping his scales and his skin from freezing solid. So it's keeping him not toasty warm, but it's keeping him from freezing solid. And he's able to withstand temperatures. Well, the glycerol production is triggered at temperatures that are like 5 degrees Celsius, but he can survive in temperatures lower than 5 degrees Celsius. Amazing.